Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to calculate the atomic mass of an isotope. So let's get into this. So in this problem we're told that natural rubidium has the average mass of 85.4678 grams per mole and is composed of isotopes rubidium-85, which has a mass of 84.9117 grams per mole, and rubidium-87, which they don't give you the mass for. The ratio of atoms of rubidium-85 to rubidium-87 in natural rubidium is 2.591. And then they ask you to calculate the atomic mass of rubidium-87. So in this video, just like in my last video, you're going to want to use the equation for finding the atomic mass of an isotope, the average atomic mass of an element using the isotopes. So let me write this down. So the one equation that you normally see has percent abundances in it. So let me write that down. So the atomic mass, this is the weighted average. This is what you would find on your periodic table. This weighted average, or we could just say, we could call it weighted average atomic mass or something like that. So the weighted average atomic mass. Again, this is from your periodic table of your element. So we would find this by looking up rubidium. This is going to be equal to the percent abundance, right? So this is going to be the percent abundance. How do I want to write this? Let's just say AB abundance, or I forgot the percent. So we'll say a percent abundance, AB for abundance for the first isotope. I keep forgetting. For isotope number one, we'll just do number one for isotope number one, multiplied by the mass of isotope number one. And then you're going to add to that the abundance and percent abundance and mass of the other isotopes multiplied together. So this would be the percent abundance of isotope number two multiplied by the mass of number two, and so on, right? You could go on, plus ... And then this would be divided by 100. So taking these together, divided by 100, that would give you the weighted average atomic mass of your element that you would find on the periodic table. So this is the equation that we're going to have to use to help us here, because they're giving us isotopes, they're giving us masses, and so we have to use this somehow. Okay. One thing I want to point out is that you can change the percent abundances to relative abundances by multiplying by 100. So, or I'm sorry, not multiplying by 100, by dividing by 100 here. So look, notice here that they're already dividing by 100. So when you take this and divide this percentage by 100, you get the relative abundance instead of the percent abundance. So built into this equation is already the relative abundance. They're just not really writing it out. So I can rewrite this. I can take the 100, divide this percent abundance by 100, and that'll give me the relative abundance. So relative abundance, so here I'll just write this out. So the relative abundance is going to be equal to the percent abundance divided by 100. And the reason for that is just to kind of spell it out a little bit more, is to get a percentage, you're going to have a part divided by a whole multiplied by 100 gets you a percentage. This is the generic equation for percentage. This part here, when we're dealing with abundances, you got a part divided by a whole. This is your relative abundance. It's a fraction. So you might call this the fractional amount. Sometimes they call it the fractional amount or the percent amount, right? Percent amount would be the fractional amount divided multiplied by 100. Well, if you divide both sides by 100, you get this. Okay. So the relative abundance is the percent abundance divided by 100. That's exactly what you have here. Percent abundance divided by 100. So if we do that, all right, let me erase this, give me some room. So then what you have is, I'll just say atomic mass here. So, or average atomic mass. I guess I can keep this. So the weighted average atomic mass of your element is equal to, and then so we're going to replace this with relative abundance. So the relative abundance of isotope number 1, oops, I forgot the 1, multiplied by the mass of isotope number 1, plus, again, percent abundance divided by 100, that's your relative abundance. So this is going to be the relative abundance of isotope number 2 multiplied by the mass of isotope number 2. And then you could add what other isotopes you have. So if you have 3 isotopes, you'd have plus the relative abundance of isotope number 3 multiplied by the mass of number 3. If you have a 4th one, then you do this same thing with the 4th one. And so notice I don't have the 100 here anymore. So this is the equation with relative abundances in it. Okay, so this is going to be useful. I could use either equation, but I'll end up using this one, and I'll explain that when I get to the rest of the problem. So here now they're giving you this, we can look up in the periodic table. Relative abundance of 1, relative abundance number 2. We have 2 isotopes, 87, rubidium-87, rubidium-85. But we don't know the relative abundances. They gave us the mass of 1, but they didn't give the mass of the other. So we have 3 unknowns. We have 1 equation. How in the world are we going to do this? Well, let's simplify. Let's look at what they gave us. One key thing they gave us is this fraction here. They said the ratio of atoms. So here, if we have a sample of atoms in our bucket, if I had a beaker of atoms, right? So if I have a sample of rubidium atoms, the fractional amount of rubidium-85 to rubidium-87 is this amount here. So that's the fractional amount of these 2, right? Of the 2 isotopes to each other. This relative abundance is not the relative abundance of them to each other, but to the whole. But we can use this to help us get that whole, right? So what do I mean by that? So let's write it out. So if I have my fraction, let's Rb, I'll have 85 over Rb-87. So that ratio they're telling us is 2.591. Well, that's the same as 2.591 over 1, right? So 2.591 over 1. So they're giving us that ratio. Okay, you with me so far? Okay. So I have this ratio. What is this ratio telling us? It's telling us that for every atom in my sample, whatever that sample is, it could be 100 atoms, it could be 200 atoms, it could be 953 atoms, but regardless, the fraction tells us that for every one rubidium-87 atom that I have in my sample, I have 2.591 atoms of rubidium-85. So for every one of these, I have 2.591 of these, rubidium-85. Well, how does that help us? Well, if I only had this amount, right? If I had one atom of rubidium-87, let's add this together. So let's say I have one atom of rubidium-87. Well, according to this fraction, I should have 2.591 atoms of rubidium-85. So I'm going to add that. 2.591 of those atoms. Well, what's the total? If I add these together, I get 3.591. So the fraction helps us get a total. So if I have one of these, then I must have this amount of this isotope here. So if I do, then I add those together and I get the total. The relative abundance, or the fractional amount with respect to our abundance here, the relative abundance, we can calculate by taking each of these, right? So let's remind ourselves, this is, oops. So I have one rubidium-87, and I have this amount of rubidium-85. So what I can do is I can calculate the relative abundance by taking this and dividing it by this, and I can get the fractional amount. So 1 for the rubidium-87, right? Let me put it this way. So for rubidium-87, the fractional amount, or the relative abundance, would be the 1 divided by not the 2.591, but by the 3.591, which is the total. 3.591. So that would be the fractional amount. It's like, remember, this is related to percentage. What is a percentage? Percent means out of 100, which is what I'm assuming to be the total when I do a percent. Well, the fractional amount is always going to be part divided by a whole, or total, multiplied by 1,000, right? So what's my part here? My part is 1. So 1 is a part, 2.591 is a part due to the rubidium-85. My total is 3.591. So I'm taking a part, dividing it by the whole. That gives me the relative amount. Now, if I multiply this by 100, that would give me the percent abundance. So here is the fractional or relative abundance. And if I find this, I get, let's see, let me calculate that. 0.27, so 0.27, what was the rest of it? 847. So this is the fractional amount, or relative abundance. If I multiply this by 100, then I get the percent abundance. So if I multiply that by 100, I get 27.847%. So this would be rubidium-87. So the percent abundance is that for rubidium-87. And then I can do the same thing with regard to rubidium-85. So rubidium-85 Or I could just, another way is I could just take this, subtract this from 1. Remember, because the all of the relative abundances add up to 1, right? Just like all of the percent abundances add up to 100. If I divide 100% by 100, I get 1. So I could take this number to subtract it from 1 to get the relative abundance, or I could take this percentage, subtract it from 100, get the percent abundance of this one. Or I could just calculate it again using this way. Whatever you want to do, you can do. So in this case, just to show it again, I'm going to take this. This is the part for the rubidium-85, which is what I'm trying to find. So I'm going to take the part, 2.591, and I'm going to divide that by the whole, 3.591. So this gives me the relative abundance, or the fractional amount. Again, if I was to go ahead and just multiply this by 100, I would get the percent abundance. So here, when I multiply this out, I should get 0.72153, 0.72153. And again, if I multiply this by 100, I'm going to get 72.153%. If you add these together, you get 100%. If you add these together, you get 1. Okay, so now that I've got this, I've got the percent abundances, I've got the relative abundances. Guess what? I can use either one of these equations. So I can use the percent abundance. So I've got both of those percent abundances. I've got the mass. I've got this from my periodic table. So I can use that. Or I could use the relative abundances, plug in the relative abundances with the mass that I'm given, and the weighted average from my periodic table, and then I just solve for the missing part. So let's go ahead and do that. Okay, so I'm going to erase, give myself some space, and I'm going to use the relative abundances because that's just the way I am. So I'm going to use this equation. So I'm going to look up the weighted average of rubidium on the periodic table. And when I do that, I get 85, 46, 78. Or I think I'm giving that in the problem. Yes, I'm giving the average mass right here, 85. So 85.4678 grams per mole. And that's equal to the relative abundance, which I got here. So that's going to be rubidium. Let's do rubidium-85 first. So rubidium-85, that's going to be 0.72153. So I'm going to have 0.72153 grams per mole. Okay. I'm going to multiply that. Oops, not grams per mole. That's a relative abundance. There's no units for this. So it's going to just be that number multiplied by the mass. And the mass of 85 they give me is 84.9117. So 84.9117 grams per mole. And then I'm going to add to that the second isotope, so the relative abundance of the second isotope, which is rubidium-87, which is 0.27. So I'm going to put 0.27847. And I'll multiply that by its mass, which we don't know. So we're going to just leave mass, and we'll just put rubidium-87. So now look, we know everything except for this, so we could easily solve this equation for the missing part. So we multiply these together. And when we multiply those together, we get 61.2663. So this is going to be equal to, 85.4678 grams per mole is equal to, what did I say, 61.2663, 61.2663 grams per mole plus 0.27847 multiplied by the mass of rubidium 87. Excuse me. All right, so now I have these together. So I'm going to move this over. So I subtract 61.2663 grams per mole from both sides, minus 61.2663 grams per mole. Okay, so I'm going to get this out of the way since we don't need that anymore. So I subtract these two, and when I subtract those two, I get 2014. So I'm going to get 24.24146 grams per mole. And that's going to be equal to what's over here, right? So that's 0.27847 multiplied by the mass of rubidium 87. So now all I need to do is divide both sides. 0.27847. Divide that by 0.27847. So this cancels out. I have massive rubidium by itself. So all I need to do is divide these two. And what I get is 86.9087 grams per mole. And that is equal to the mass of rubidium 87. And that, ladies and gentlemen, is how it's done. So if you like this video, if this helped you out in any way, then please make sure you like the video, share the video, hit that like button somewhere over here. Also, make sure you subscribe to the channel. But before you do that, please put a comment down below and let me know what you think. When you subscribe to the channel, hit that notification bell. When you do that, make sure you click all so you'll be notified by all the videos I put out. And finally, when you put that comment down below, let me know what you have a question on. If you have a question, if you have a problem you need help with, or if you have a topic you want me to cover, put that down below. I would love to do that for you. Thanks for joining me and have a great day.